colored layers in there are horizontal. That is a fundamental principle of geology, is that sediments begin as horizontal layers. Rivers do it, ocean does it. So deposition in a body of water, because of the way gravity works, tends to form horizontal layers. Now we can try to mess it up and say, well, what if I hold it like this? Well, you still wind up with horizontal layers in that thing. And maybe you say, well, how about if I could make a tilted layer and then just barely sort of move that, and then I got a permanent tilt. But eventually this thing collapses back into horizontal. That's just how gravity works. So understanding that, first off, that sediments begin as horizontal layers. So when we see something, that said recording has started. And I guess I started recording without knowing it, because it says it's going. So you're being recorded. And that's good, because I forgot. So I'm going to go to the slide here that was up earlier. You're looking at. So when you see an exposure of sedimentary rock, which this is, and notice that none of the layers there are horizontal, we realize a couple of things, obviously. We realize that those sediments must have been cemented together before something caused them to be tilted. This section over here is composed of vertical sediments. They're not horizontal anymore, they're vertical. Well, that will only work if they're held together when they become tilted, because if I tilted this, they'll slide down. The second thing you notice about this is that there are two sets. There are two sets of sedimentary rock there at different angles to each other. So that tells us that if this top layer was present when these others went from horizontal to vertical, if that had been present, it would have gone to vertical as well. So this wasn't even around when this happened. So we're looking at least 2 episodes of sedimentary rocks being yoinked from horizontal. That's fairly important. We could see this at hundreds, if not thousands, of places across the globe. One good example is the Grand Canyon. You'll notice that the Grand Canyon is composed of thousands of feet of horizontal rock. Till we get close to the bottom in this view, and you see that there are some that are at an angle to that horizontal rock. Well, from our experience with the sedimentator, we know 2 things. We know, number one, that those sediments had to be cemented together before they were tilted, or else they would not have held together in that way. And number 2, that all of those horizontal layers above that were not present when they were tilted. So once again, we're looking at least 2 different episodes of things. And this is very important, because in the late 1700s, the Western world, and by the Western world, I mean Europe and the Americas, believed that the Earth was about 5,500 years old. Oh, I hear a beep like someone's waiting to get let into the lobby. So let me see. Nope. Nope, they made it in, it looks like. Sorry about that. Oh, is anyone else having trouble hearing me right now? Okay, so it would appear, Brenton, that the problem is probably on your end, unfortunately. So you might have to troubleshoot that a while, and meanwhile turn on the captions. And this will be recorded, hopefully. So it was pretty much accepted. Oh, I'm sorry. What's that? Okay. It was pretty much accepted as fact that the Earth was 5,500 years old. And so scientists, because this was really, really accepted, and we know what happened to certain people when they tried to go against the prevailing dogma of the day. Galileo famously almost was put to death for saying some astronomy thing that turned out to be right. I'm sorry, I'm not an astronomy professor. So in order to fit things that we saw on the planet, like the Grand Canyon or the Himalayan mountain ranges, mountains that go 5 miles above sea level, and to think about how they were formed in just more than 5,000 years, we had to start inventing. Geologists had to invent catastrophes. And so the school of thought for the day in the late 1700s was called catastrophism, because we would say, well, how were the Himalayas formed? Well, there's only 5,000 years to do it in, so it must have been thousands of feet at a time uplifted. How about the Grand Canyon? Well, it must have been an enormous flood, several orders of magnitude than any that we have ever experienced or that we have any evidence for, that laid down thousands of feet of sediment in an event, and then as those waters were draining away, it carved an enormous canyon. Today, we know that there is no evidence for those sorts of things. And in fact, many of those things are not possible using the forces that the Earth operates under. But at the time, that's what you had to do. You had to invent these kind of wild sounding events that there was no evidence for. And James Hutton in the late 1800s, sorry about that, he had a problem with that. He visited areas all around the coast of Great Britain with his rock hammer there. And one of the more famous ones is Sycamore Point. There's a little, looks like a computer rendition from 1985 of it, but we have seen the photo. That is Sycamore Point, and it's famous among geologists because he visited that, and he realized that what we were looking at was you had to have sediments laid down, then they had to be cemented into rock. They had to be buried deep enough to be cemented into rock. Then they had to be yoinked vertically, and that tends to happen deep in the earth. Then it had to be eroded off. And then the whole thing went over again with that second set that's sitting on there. He was seeing this time and time again, and many places have more than 2 episodes. They have 3 or 4 even. And he realized that 5,500 years was not enough time to explain these things without evidence of catastrophism. Hutton's idea was that why couldn't these things have formed using the processes that we see around us at normal rates, at the rates that we see them happen. But in order for that to be true, the Earth had to be much, much older than people were saying. And so Hutton's idea was not very well accepted at first. He wrote a book. This was a radical idea at the time. And he wrote a book about it. He explained in these figures here how he thought that this happened. To him, there was evidence for these things being formed the way that modern things are formed. And there was no evidence for the catastrophes. One of his ideas is now known as gradualism. So on the one end, you got catastrophism, things happening, just crazy events happening in, enormous things happening in short time, versus gradualism, a river gradually eroding a canyon over long periods of time. So he wrote a book, and there were a couple of problems with that book. Number one, it was 2,000 pages long, and very few people then or now read 2,000-page books. Another problem, as you see, is the prose was extremely dense. It was really hard to hack through his writings. He was not a talented writer. He was a talented thinker, not a talented writer. So Hutton went largely ignored. Even the title of his book was 4 lines long. So he had a problem with it. He needed an editor. Playfair came along a couple of decades later and read Hutton and realized that there were some really good ideas hidden in all that dense prose. And he wrote a paper about this. And a couple of decades later, a guy named Charles Lyell discovered Playfair, which led him back to Hutton's original book. And Lyell was a talented writer. And he wrote a book called Principles of Geology that's now famous among geologists. He wrote Principles of Geology, which we recognize now was sort of like Hutton for dummies. He took Hutton's ideas, distilled them into a form that was easily digested by general public. As a result, it made Hutton's radical at the time, but actually very, very rational and sensible ideas, made them easily available to the general public. So this became a bestseller. It went through numerous printings. It was a hot book around the 1830s. Whatever Twitter was back then, he was trending then. It was extremely popular. Everybody was reading Lyell. And so everybody was getting into Hutton's ideas, and they were realizing that things just made a lot more sense going with gradualism. Well, one of the things that this was called is uniformitarianism. It's a really big word, but uniformitarianism is what they were calling it back then. It's what we still call it today. Now, your textbook tries to go with actualism. Your textbook tries to say actualism, but I learned it as uniformitarianism. And to me, uniformitarianism tells more about what is going on. When we talk about uniformitarianism, it's popular to say the present is the key to the past. And what that means generally in a nutshell is that we can observe things happening today that will help give us clues about what happened in the past. Let me do that in a little bit more detail. So what it means is that if you look at something like the Grand Canyon or the Himalayan mountain range or the Ozarks that we are in, excuse me, that means that no one was around to see those form. Sometimes it's because it took them millions of years to form, and sometimes it's because it happened millions of years ago, and sometimes both. So no one knows exactly how they were formed because no one saw it. But what we can see is modern day geologic processes. We can see present processes. Have you ever observed a geologic process? And the answer is, of course you have. Have you seen have you seen video of volcanoes erupting? Have you seen videos of floods? Have you seen a river in flood? Have you seen what a flood leaves behind? It leaves behind sediment. So it's very easy for us today to observe geologic processes and their results. And what else we observe all around us are the results of past processes. What's missing in all this is the past process because no one was able to observe that. But uniformitarianism states that we can use the present day processes and results to make educated conclusions about the past processes. What we say is that similar results are likely to have been caused by similar processes. And maybe a more succinct way of saying that is that similar processes produce similar results. It doesn't mean that they absolutely were caused by the same thing, but it means that the best data we have is watching things occur today, watching processes and the results, and then comparing ancient results to modern results and saying they were likely caused by the same thing. Let me give you an example. I don't know if any of you have children, but if you do, maybe if you have a 5-year-old or had a 5-year-old at one time, and that child goes to play at a friend's house and then comes back with this stain on his shirt, and you say, "What is that stain?" And the kid's answer is always what? "I don't know." You know, when you're 5, it's really not your job to keep up with stains and stuff. You're more interested in playing and stuff. So what you have here is a result of a process that no one's really sure about. The result is the stain. The process is we don't know. So it'd be helpful to see something like that happening in front of us. And it just so happens, let's just say that a week from now, you go to pick your son up from the same person's house, and this time he and his friend are on the steps eating chocolate ice cream cones, and of course it's dripping down their hands and their arms, and he's rubbing his arm on his shirt because we don't like the feel of that. And you know, it may have dropped off the cone and on that, and you see this time, you see that eating a melting ice cream cone causes a brown stain on the shirt. That stain is really similar to the stain that you saw a week ago. So what is the most logical conclusion that you would draw from that? The most logical conclusion, the most sensible, the simplest explanation is that the stain a week ago was also from chocolate ice cream. Do we know 100% for certainty? No, we don't. But that is based on the data. That's the best thing we have going. What about geology? How does that apply to geology? Well, let's say that you visit Hawaii one day, which would be cool. We'd all love to do that. And you pick up a rock while you're on vacation there. You're on the Big Island and you pick up a rock and it's black or dark gray. It's a black rock. It's a heavy rock. It's dense. It's hard rock. And you say to yourself, I wonder how this rock was formed. But who knows when it was formed, much less how it was formed. So once again, you have a result of an unknown process. But the next day on your vacation, you go visit, on the same island, you go visit Volcanoes National Park, where you find that you get to see Kilauea erupting. And it's been more or less erupting on and off since 1980, 1981. It's been erupting on and off, and you get to see lava flowing out of the ground and then cooling off into and hardening into a black, dense, heavy, hard rock that looks really, really similar to the one that you saw yesterday. So what you have now are you have two similar results, but what you have that you didn't have yesterday is you have a process. You saw this modern rock being formed. So what are you going to say about that rock? You're going to say similar processes lead to similar results. So it's likely that the rock I saw yesterday is also a lava rock. Do you know with 100% certainty at this point that it's a lava rock? Only way to know with certainty would be to be able to go back in a time machine because no one saw it happen. But based on the data you have, the simplest explanation and the best explanation is that, yes, it was a lava rock. Is it possible that someone tossed yesterday's rock out of an airplane and it landed on the island? It's possible. Does that seem likelier than it cooled from the volcano that the island is made of? No, it does not. So that's what uniformitarian is about. And all of our landscapes and features of the planet around us, most of them, not all of them, but most of them make a lot more sense when we think about them as gradually forming using today's processes. There's no reason to think that processes in the past were different than processes today. Gravity works like this. Is there reason to believe that millions of years ago gravity worked sideways? No, there's no reason to believe that because we know that gravity works towards the center of things. So with Lyell making this idea really, really popular, the Western world pretty much dumped catastrophism. Now today we realize that that occasionally there are really, really large catastrophes, such as a 6-mile wide meteorite hitting the Earth causing mass extinctions. Occasionally these things do happen. But for things like a flood big enough to lay down the entire Grand Canyon sediments in one sitting, we have trouble with there even being enough water on the planet for that to have happened. So Yes, there are a few catastrophes, but everything is much better explained. It's more rational. It's more level-headed to explain using gradualism. So everybody realized 5,500 years wouldn't do it. And every prominent Western scientist of the day tried to figure out using all these different methods, what is really the age of the earth? They'd look and say, okay, how long does it take a river to lay down sediment in normal flow? And they'd say, okay, then it takes this long, and they'd calculate back. And they came up with quite a wide array of numbers. But they were all wrong. And they were all way, way still overestimating it. Even some people that said 300 million years old were still underestimating it. It wasn't until the very end of the 1800s, the beginning of the 1900s, till Marie Curie. Now, her husband, Pierre Curie, was working with her, but you don't usually hear much about him. So you get the idea that she was the brains of the team, and he was just kind of a test tube washer. But she discovered that radioactive isotopes will decay at a constant rate. And there's a section in the book in chapter 8 about that, but we're not going to really get into that. But what that means to us is that most igneous rocks and most metamorphic rocks, not so much sedimentary rocks, but most igneous and metamorphic rocks have radioactive elements in them. And when a radioactive element forms, so let's say when magma cools off into a hard rock, that's like a stopwatch starting. It's like you click it on and it starts ticking. When radioactive elements form, they are, the element is 100% radioactive, but it immediately starts decaying. If you're familiar with the term half-life, it immediately starts decaying to a stable daughter product. And it does that at a constant rate. So all we have to do today is measure what is the ratio of radioisotope to the non-radioactive isotope. When we do it with carbon, it's called carbon dating. Carbon doesn't go back enough to use in most rocks, so we use other isotopes like potassium argon. But we simply measure the ratio of how much is left, and we know how long it took for this to convert to the other. It's actually a simple mathematical equation for us to figure out how long that rock has been a rock. And after doing this thousands and thousands and thousands of times, we have arrived at a consensus that the Earth is 4.55 billion years old, and that's rounded up to 4.6. So that is billion, not million, which is much greater than any of the scientists before Curie were coming up with. Now, so that's one number that I will ask you to give me on an exam. I do not ask you to memorize numbers in this class except that one. That is an important number to us. It is an important number, but geologists are actually more concerned with relative age. And by relative age, what I mean is if we visit an exposure of rock, like maybe Sycamore Point that we saw at the very first slideshow, or the Grand Canyon, we want to know in that exposure of all those different layers, we want to know what is the oldest, what's the youngest, what's the second oldest, what was the sequence of events that happened there. So that's really what we're more interested in, is the relative ages. So in doing so, geologists have come up with 5 relative age principles that we use to determine relative ages at a site. And the first one, we've already demonstrated. It's called original horizontality. And it is that sediments usually begin as horizontal layers. Almost always. There's slight exceptions to this, but sediments begin as horizontal layers. That's just what gravity does. So we've already demonstrated original horizontality. That's the first principle. The second principle is called superposition. And superposition is logical. It's extremely logical. A few students struggle with it, but eventually they come around. I'm going to use a different metaphor at first. Let's assume that when you throw away dirty clothes for the day, that you just put them in a pile somewhere. Or maybe you have a laundry basket, but you throw them in that laundry basket. Where are you going to find the clothes that you wore the last time you did laundry? Where are those going to be located in that basket?
In the bottom.
Exactly right. They're going to be on the bottom. They're going to be on the bottom of the laundry basket. Where are you going to find the ones that you wore last night?
The top.
At the top. That's superposition. So where are you going to find the oldest rocks? At the bottom. If we have a laundry basket, we don't scoop out all that laundry to put something underneath it. I don't know, maybe you do, but that's not how most people, I think, do it. And gravity doesn't work that way either. Gravity does not take an existing layer of sediment or rock and somehow lift it up and scoot sediments underneath it. When you build a sandwich, you don't smear peanut butter on a plate and then try to slide a piece of bread underneath it. When you build a sandwich, you lay down bread and then start putting things on top of that. So the oldest part of that sandwich is at the bottom. That's the first thing that was laid down. And that's superposition. Superposition, stated simply, is that rocks in a sequence get younger towards the top. Another way to say it is that rocks in a sequence get older towards the bottom. Old stuff's on the bottom, younger stuff is on the top. I want to say one more thing about that laundry basket. If we're talking about sedimentary rocks, remember that you can't date those. We just know relatively this is this is younger than the one below it, and then this is younger than the one below it, and so on. But what if you pulled out a pair of pants in the middle of that laundry basket that has a receipt in the pocket? What can you get from a receipt? There's usually a date on that receipt. That tells you the actual day you wore those pants. So if you've got a sequence of sedimentary rocks and there happens to be a lava flow in the middle of that, the lava flow can be dated. And so we can get an absolute age. We can at least tell that everything underneath that lava flow is older than that lava flow and everything above it is younger. And we know the exact, let's say that lava flow is 35 million years old. We can do that. So occasionally we are able to date sedimentary rocks if there's enough other igneous things around. So again, superposition, all the stuff on the bottom get younger all the way to the top. If we look at a slice of the Grand Canyon, where are you going to find the youngest rocks?
The very top.
Yeah, the very top, on the rim of the Grand Canyon. And the oldest ones are going to be at the bottom. Third principle is called cross-cutting relationships. So sometimes things will cut across a sequence of rocks. These things could be fractures or they could be fault lines. They could be dikes, which are little fingers of igneous material that winds up inserting itself across layers of rock, shooting itself along cracks in between. So let's think about the sandwich again, or think about a cake. What's older, a cake or a slice of cake? The cake has to exist before you can take a slice of it, right? A sandwich has to exist before you can cut it in half. So cross-cutting relationships say that anything that cuts a sequence is younger than that sequence. A sequence is older than anything that cuts across it. Two ways of saying the same thing. Fourth principle. Fourth principle is the principle of lateral continuity. And by that, we simply mean if we look at the Grand Canyon yet again, and we see one of the units that we see there is a really prominent white rock there. Well, if you were to visit the Grand Canyon 30 miles down the road, then you would still see this white rock unit. And you would see that rock unit that's below it, and you'd see this one that's up above it there. And you might even leave the Grand Canyon and still see those rock units. That's what we mean by lateral continuity. It means that these rock units tend to stretch horizontally for a long way in all directions, tens of miles, sometimes hundreds of miles, until they do eventually get thinner and thinner and pinch out, and they're replaced by some other rock unit. That's all that lateral continuity says. But using these four principles, we could visit a place like that. And I know I said 5. We're not at the 5 yet. But using these 4, you could visit an area where there was a bunch of the rocks exposed, and you see a bunch of superposition and original horizontality and stuff and cross-cutting, and you could exercise those principles and tell which thing is older than which thing. And you could actually pick any 2 things, and most of the time you can tell which one is older than the other. You can do an entire sequence of events. In fact, your textbook goes through about 3 pages of going step by step. What happened first, what happened second. I do want to make sure that most of us are on the same page here, though. So if I was to ask you between 2 units here, and use the chat window if you'd like, but between the Hamlinville formation and the Foster City formation, which one of those, what did I do? I kind of lost my team's window for it. Hamlinville and Foster City, which is the older unit?
Foster City.
Okay, most of you agree that it is the Foster City formation. Why do I keep losing my team's window? I'm going to have to bring it back somehow. And there it is. Okay, I've got it back. Okay, how about Hamlinville or Skinner Gulch or Hamlinville? Which is younger?
Skinner Gulch.
Skinner Gulcher.
Skinner Gulch is on top, right? It's got to be younger. Okay, how about the dike or granite? One of those cuts across the other one. They're located right about here.
Dike is younger.
The dike is younger. The dike has cut across the granite. The dike has also cut across the Larsonton, which makes it younger than the Larsonton, but it was not able to cut across the Foster City formation, likely by the way it's cut off there, likely because the Foster City formation wasn't even there when that dike pierced through the rocks. So that dike appears to be older than the Foster City formation. So the Skinner Gulch is the youngest rock unit there. It is the youngest rock unit. But is it laterally continuous?
No, because it cuts off.
It's cut off right here, isn't it? Now, it certainly looks like across the canyon, we pick it up again. But apparently something has cut across the Skinner Gulch limestone, and that something was a river that carved a canyon out. So what's younger, that river or the Skinner Gulch limestone? Obviously, the canyon is a much younger unit because it has cut the Skinner Gulch into the Skinner Gulch on that side of the canyon and the Skinner Gulch on that side. It's real common for you to look across the canyon and see the same stuff that is at your feet. So that river is flowing today. Any river you visit is currently doing geologic stuff while you're at that river. If you stand in the river, it's moving rocks around. So it's doing stuff actually today. I'm going to check the chat really quick, see if there's any questions right now. Everybody's pretty good with those 4. I did it again. Dadgummit. It takes me a while to get my team's window back when I kill it. So using those 4 age relationships, those 4 principles, we can determine the age. What about that 5th one? Okay. Well, remember standing on the edge here and looking at your feet and saying, oh, I got the Hamlinville just below me, and then I got the Foster, and then I got the Larson. And I look across the canyon and I can see that it looks like I've got those same 4 units in the same sequence. Doesn't it look an awful lot like these 4 were at one time connected like a cake, but they have since been cut by the canyon. It's almost like someone took a cake and instead of taking a slice out the side, took a big V-shaped slice out of the top, so that the stuff on that side and that side are the same. They've just been removed in the middle. What you do when you say that, when you say, oh, I bet that's the Skinner Gulch, I bet that is the Hamlinville, I bet that's the Foster City, that is called correlation. And the difference between correlation and the other four is that with correlation, we're using more than one location. We're comparing the age of the rocks here with the age of the rocks somewhere else. Maybe it's Bentonville versus Fayetteville. Maybe it's Bentonville versus Mexico City. Maybe it's Bentonville and Beijing. It could be anywhere. It's comparing the ages of the rocks at one place to the ages of the rocks at another place. And if you're lucky, you can correlate visually, like we did across the river here. There's places in Bella Vista that I can correlate visually. I can stand on one hill slope and look across the valley at another hill slope and see it's the exact same units on either side. So that's easy correlation right there. But most of those instances I mentioned, you can't stand at one rock exposure and see the other one. Is there any place in Bentonville that you can stand and see rocks in Fayetteville? Of course not. It's too far. There's a little curvature of the earth involved as well. Certainly we can't see from Bentonville to Beijing. So in those cases, it's a little trickier. So correlation, I jumped the gun a little bit. Let's go ahead and define correlation. Correlation is determining age relationships between units at two different localities. Let's not say even, let's not restrict ourselves to two. Let's just say at different locations. I apologize for the blue there. It looks like it's hard to read, but that says at different locations. If you cannot see the next exposure of the unit or units that you're looking at, then you could get into trouble. Because, for example, there are two different units in the western U.S. called the Coconino Sandstone and the Navajo Sandstone. And when you visit each one separately, they look exactly alike. They look exactly alike. So you might visit one and then drive to the other place and say, oh, that's that same rock unit I saw before. When in reality, if you were to drill a well right here, you would come across the Navajo Sandstone, then you'd go through a whole bunch of other layers and eventually come across the Coconino Sandstone. You'd say, uh-oh. Is this the Navajo again? It must be a different one because it's much lower and therefore much older. Turns out that Zion Canyon is higher elevation than the Grand Canyon area. So they are two different ones. Ultimately, to do true accurate correlation, you need to have fossils. Because fossils are what? What are fossils? Fossils are remnants of organisms. They are remnants of living organisms. Just about anything can form a fossil. We have algae fossils. We have bacteria fossils, although those are, I've not seen a bacteria fossil, but they do exist. They're hardly distinguishable from something else. Here's the thing about fossils. Let me back up. Here's the thing about organisms. Organisms tend to not remain the same over time. Now, some things do. Alligators hadn't changed much in several hundred million years. Some sharks have not changed very much at all. And so something that doesn't change very much over long periods of time, that's not useful in correlation. But something that does change its form as it evolves is very useful. So on the left-hand side of this figure, we have a stack of rock units, oldest on the bottom, of course. And what we're showing is an organism that over time is evolving into a different form. It's a nautilus that started out with a straight shell, and then that shell started getting slightly curved, over time a little more curved. There was some advantage to that organism for doing that. So it gave birth to more other organisms, and eventually it became a very coiled shell. So if you find this fossil anywhere else on the planet, it could be a continent away, an ocean away, then we know that those rocks that where you found this are the same age as the rocks at this location. If you find that fossil somewhere else, because that fossil only existed for a short period of time, if you find that anywhere else in the world, we know that that rock correlates to those other ones. So we could do that. We could correlate between Bentonville and Fort Smith, and we could real easily tell that the fossils in Bentonville are older than the ones we would find at Fort Smith. They are more evolved, if you will, at Fort Smith. And that's calling them more evolved is really not a very not a good way of putting it. But hopefully you get the idea. These fossils that do change frequently over time, they enable us to give us a little snapshot in time. And remember that laundry receipt, the lava flow. If one of these, instead of a sedimentary bed, was a lava flow that we determined was able to date and determine that was 25 million years old, then that would tell us that these were all older than 25 and these were all younger than 25. Now, whenever we see this fossil there, we say, oh, it's younger than 25 million years old. And if there's another lava flow on top there dated to 20, well, man, we can really start putting dates to those fossils. So geologists have been correlating across oceans and across continents for 200 years now. William Smith in England first started doing all this correlation. They've been doing it for hundreds of years now. And eventually they came up with a very refined, what we call the geologic time scale. And this is a fundamental thing to all introductory geology classes worldwide, is the geologic time scale. Now, the one that I'm showing there has one error on it. Let's not call it an error. It's outdated. There is a period near the top called the Tertiary. And just a few years ago, the International Congress of whoever decides these things decided that the Tertiary needed to be split into two. So right now, we are trying to get rid of the Tertiary period and everything and replacing it with the Paleogene and the Neogene. The Tertiary has been split into two periods. What I want you to know for an exam is the three eras. And these all stand for, Zoic stands for life. So Zo means life. So Paleo means ancient, Meso means middle, Sino means recent. So the era of ancient life, the era of middle life, and the era of recent life. So the three eras and the periods that belong in them. From oldest to youngest, it goes Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian, Triassic, Jurassic, Cretaceous, Paleogene, Neogene, Quaternary. If I can do it, you can do it, at least for one exam. We are currently in one of those periods. We are currently living in the Quaternary time period. If a river somewhere floods tomorrow and leaves behind deposits of mud, we say that those deposits are Quaternary in age because we sit at the very top of that. So I do not need you to know any of these dates, and I do not need you to know any of these subdivisions here, and I do not need you to know any of these subdivisions here. Just these periods and the eras that they go into. This is on page 200 of the most recent edition of your textbook, the 16th edition. This is on page 200 for your reference. But before I go much further, let me discuss a few things about some other things on this thing, on this time scale. If you notice, the things that I asked you to know start right here. Well, if you put those to scale with the rest of the time period, you notice that they make a really, really small portion of the overall time scale. If the Earth is 4.5 billion years old, I'm only asking you to learn the last 500 million. So a really small portion of it. Why is that? Everything before that, geologists tend to lump into the Precambrian. Now, some geologists that specialize in these things, they will talk about the subdivisions of the Precambrian. But me and others, we just lump it on the Precambrian. Why? Because as far as life is concerned, there wasn't a whole lot going on then. For the first billion years or so, there wasn't any life, and then for the next 2 or 3 billion years, it was mostly single-celled stuff. It was algae and bacteria. Every day, just like the last, algae and bacteria for 2 billion years. It wasn't till close to the end of the Precambrian period that these things started evolving into multicellular organisms and also started using hard parts. They started creating shells from the ions that they would pull out of the ocean water. So they started doing this, and there appeared to be an explosion of life at the start of the Cambrian. Now, I'm going to swing over to here, and this is a figure taken from chapter 1, but it really makes more sense for us to talk about it in chapter 8. We're going to do chapter 1 next hour, but we're not going to really talk about this. So this has a few milestones on it. So this tells you what was happening. Earliest single-celled fossils at about 3.5 billion years ago. And then the first really abundant at the start of the Cambrian. Then fishes in the Silurian were really abundant. It's often called the age of fishes. In the Devonian, we had our first land plants. And then first reptiles were happening in the, I want to say that's the Pennsylvanian, first reptiles. And by the end of the Permian, you had some really small mammal-like creatures. At the end of the Permian period was the largest mass extinction in the planet's history. Now, most of us are familiar with the dinosaur extinction. That was the second largest. The largest, the general public doesn't know much about because there wasn't anything really cool like the dinosaurs that died out then. It was a bunch of unknown sea critters for the most part that died out. But 95% of everything that was alive did not make it. And we think that that was from a series of volcanic eruptions that happened over thousands of years that put so much gases into the atmosphere that it changed the chemistry of the atmosphere and the oceans and changed it too fast for most of the organisms to adapt. And after those mass extinctions, the reptiles grew really big, the dinosaurs, and then at the end of the Cretaceous period, meteor collision, and maybe helped by some more of those similar volcanic eruptions, 75% of everything that was alive during that time were wiped out, including most of the dinosaurs. Now, when I say most of the dinosaurs, most people believe that the birds of today are really just dinosaurs. They're so closely related to dinosaurs. They branched off of them fairly early, but they are they both branched off of reptiles, but dinosaurs did first, and then the birds branched off of the dinosaurs. So those are left with us. But of course, the dying out of the dinosaurs, when that happened, biggest mammal was a possum probably. And so, of course, mammals are much, much larger today. We have elephants. We used to have bigger land animals than mammoths. We have the largest animals today that have existed on the planet, as far as we can tell from fossil evidence, is the blue whale. Maybe not the largest organism. They say that some aspen groves are all the same organism. And I've also seen somewhere that there's underground funguses that stretch for acres and acres, but we wouldn't consider those animals. Those are plants and fungi. So this is just kind of for fun. I'm not expecting you to know when these things were happening, but I do want you to know those things. This come over someday thing is just a mnemonic. It is if you have trouble memorizing the time periods, you can remember their abbreviations by saying, come over someday, maybe play poker, try Jeff's crazy pizza nacho. Okay, so those words stand for Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian, Triassic, Jurassic, and so on up to the Quaternary. There's hundreds of those if you wanted to research. If you didn't like that one, you can find those. So that may be a helpful memory aid for you. So finally, a little perspective. When we think of time, we're used to thinking of time in the context of how long a country has been around, or how long your great grandma lived, or how long ago was it that your ancestors came to live in the place that you live today. And so these are things like 80 years, 200 years, 700 years. How long have people been writing down history? 4,000 years, 5,000 years, something like that. Well, if you took all the geologic stuff that happened in human recorded history, the Earth would look extremely similar to the way it does today. You go back 5,000 years and most of the features, the Himalayan, the Grand Canyon, the Ozarks, you name it, they're all going to look very similar, because most of those things that happened, most of our Earth's landscapes and landforms happened much sooner and took a lot longer to form. So we want to start thinking of time in a much deeper manner. One way that they illustrate it is by saying that if the Earth's history, starting at Los Angeles, is 4.5 billion years ago, if the Earth's history is a straight line trip from LA to New York, then human recorded history is not even halfway across the street in the last part of the voyage. So 2,000 years ago is a sidewalk. So this is the history that we're used to thinking about. The history. If you take history class, that's what we're thinking about. And all that's compressed into a tiny thing. Well, things were happening in the Earth during these times. And that's the times we're going to be studying. The Mississippian, the Pennsylvanian, those guys are in here. The Cretaceous period is in there. A second way to look at it is if the Earth's history was a movie that lasted 2 weeks, recorded history would go by in the last 3 seconds. So one of the things we want to do is think about things taking a really, really long time because of gradualism. Last thing in this slideshow are the takeaways. I want to remind you that the takeaways are different from what's in the study guide, but there is usually some overlap. So don't ignore either one. Again, the takeaways are more like, what did we learn today? What's a synthesis of what we learned today? The study guide is a little bit more less abstract. It's more concrete on, hey, this is what's going to be on the test. Chapter 8 has okay, there's no new questions. Looking good there. Chapter 8, you have a quiz available now for Chapter 8. Of course, it's not going to be due until our first exam, but you do have a quiz available for that now. So currently there's Chapter 2 and Chapter 8, and Chapter 1 is also available. Can just go ahead and tell you that. And of course, that lab safety quiz. So those are all available for you to do now. Any questions before we break? I'm going to turn off the recording. I'm going to turn off my camera and my mic, but I'm going to leave the window open so you can still ask me chat during the break. I'm going to be working on this and that during the break. And when this recording gets done, I'm going to post it into Canvas below the slideshow. So I'm going to stop recording now, and in 15 minutes, which should be 13 after 1, we'll get started on Chapter 1.